Hi students, today we're going to talk about factorials, and we're going to start Permutations Part 1, which is talking about distinguishable objects. Now that word distinguishable means that if I have two different things, they are definitely different in some way. They are not the same object twice. Like I can definitely tell the difference between one and the other. Alright, so here we get going. This is brand new for us, and this would be really, really great on a study sheet, so I'm going to put that on a star right there. Factorial notation is represented as n exclamation mark. So we're really excited about this n. That's what that exclamation mark means. Here's a little definition, a math definition, for what a factorial looks like. What we do is we start off with the first number with n, and then we multiply by one number smaller than n. So let's say this was 8 factorial. We would have 8 times by 7 times by, you could probably guess it, we're going to go 1 less than that, so 2 less than n. And we would just keep counting down until we get down to 1. And we stop at 1. We define, I'm going to put a little star here, we define 0 factorial as equal to 1. Alrighty, so that's what a factorial looks like, and I'm going to show you where we're going to use it in a moment here, but we're just going to practice evaluating it and doing some calculations with it real quick. So, evaluate the following. 5 factorial. I start off with 5 times 4, 3, 2, 1. And we stop there when we get down to 1, because if we went down to 0 and then all the negative numbers, we would be going on forever, wouldn't we? Then I'm going to use my calculator, multiply this real quick, 120. Let's start with 8 factorial. So we start off with 8, 1 smaller, until we get down to 1. Now in your calculator, I'm going to grab a calculator here. You do have a button for this on most scientific calculators, because let's say I gave you like 10 factorial. That might take forever to put into your calculator, and I'm kind of lazy, so I like to do things quickly if I can. Alrighty, so let's take a look on your calculator, and every calculator is a little bit different, right? But what we're looking for is something that says exclamation mark. And I see mine right here. You see it's in yellow. Mine is in yellow. So what I have to do is I have to go 8. To get to the yellow, I have to hit the shift button here, and then that button, and now it says 8 factorial. You'll notice this button right here, NCR and then PCR, those are also really important ones for us too, right? So these are kind of the buttons that I will be using in this unit for this stuff in my calculator. So that equals 40,320, and we could totally double check that just by multiplying it out real quick in our calculators if we wanted to. All right. So here's the thing is your calculator only has so much memory space. So when you put really big numbers in, it actually can't do it. So let's say I put like 1,000, 10,000 factorial into my calculator. Let's do 1,000. It says math error because that number is going to be really, really big. It's just too big for my calculator to handle. So there will be times when we do kind of have to do this by hand, or at least think it through by hand and then finish it off with the calculator. So that's why that's kind of my segue into here, where we're going to think about this a little bit instead of just going straight to our calculators. And we go down here because I feel like I have more space. Okay, so 10 factorial. Now I know 10 factorial is 10 times 9 times 8 times 7, yada yada. And I know that 9 factorial, so on the bottom of my fraction, would be 9 times 8 times 7 times 6. Now what we know about fractions and about multiplying things is that if I have a multiplicative factor on the top and on the bottom, I can divide those two things. And I'm going to put this in quotation marks. I'm using like my quotation mark hands here. We can cancel them. So 1 divided by 1 is 1. I'm going to cross off because I'm canceling it. 2 divided by 2, 1. 3. And there's a lot of these very similar numbers here, aren't they? Aren't there? So if I divide to equal 1 with all of these things, I'm just left with 10. Because 9 divided by 9 would be 1. And 10 times 1 is just 1. So you can pause here if you want to think about that for a second. And I'm going to keep going on to the next one here. Again, when I divide, a bunch of this stuff is going to divide to equal 1. Now I do have to be careful about where like the remnants are, right? And I do have to be careful about canceling, because so often we think about canceling equaling 0, but that's not true, right? Canceling equals 1, because 5 divided by 5 equals 1, not 0. So on top, I equal 1, and on the bottom, I still have some stuff left over. 7 times 6, which is, of course, 42. But I do have to be careful, because that's on the bottom of the fraction, not on the top, right? And we could do it one more time. I'm going to do it down here, so more space. And we could apply that to anything, can't we? Ooh, not a lot of space. Now this one I think acts just like you would expect it to. 8 factorial, 4 factorial just means 8 factorial times 4 factorial. So I went from 8 down to 1, and then I went from 4 down to 1. And a lot of these both on top and bottom of this fraction. And then there's some leftover stuff. It's much more reasonable to put in my calculator. Now, I think your calculator could probably do 12 factorial. I'm sure it could. But we do want to practice doing this by hand, because there will be times when I'm going to give you a number that's so big that your calculator won't handle it. So we need to really have a great understanding of how factorials work to be able to go ahead here. All right, let's take it up a step. So flip your page here. What if I didn't just have integers? What if I had unknowns like n? We're going to approach it the exact same way, starting with kind of the definition of a factorial. So n factorial would be n times by n minus 1, 1 less, n minus 2, n minus 3, and I don't know how big n is, but I'm just going to kind of say it goes on for a little while. So I'm going to put some dots here, because it's just going to continue until it gets down to 1. And I don't know how long that's going to take, but just to remind myself that there's more to go here. Now on the bottom, let's be careful about this one. My first term is n minus 2. And a factorial says that the next number will be 1 smaller than that. So n minus 2 minus 1 would be smaller than that, right? So n minus 3 would be the next thing. 1 smaller than that, n minus 4. And you get it, there's a dot there, right? Now, what I can see here is that some of these terms are the same on the top and bottom. I wrote down an n minus 4 as kind of my last term here, and I know that there's going to be an n minus 4 here as well. Maybe I'll just add that in there. So I can see that all the rest of these things, whatever comes next, they would both be on the top and bottom, which means we could divide to equal 1, and then they would cancel out. N minus 4 divide to equal 1, n minus 3, n minus 2. So what am I left with? N times n minus 1. There we go. That's much simpler than this crazy factorial expression, right? We could multiply that out if we wanted to, or just leave it there. They didn't tell us what to do, so we'll just stop. Let's try one more here, and then we'll talk a little bit about permutations. So, n minus 4 factorial divided by n minus 5 factorial. So I'm just going to write down a couple just so I can kind of get a good idea. I know I start with n minus 4. I want to go 1 less than that. So we're at negative 4, minus 1 would be negative 5, so n minus 5. N minus 6, and then kind of dot. I don't need to go forever, just enough so I can get an idea. Now on the bottom, going to start with n minus 5, and we're going to get one smaller, so n minus 6, and then continue. And you can see that whatever's next would be on the top and bottom. A bunch of these things divide to equal 1, and we're left with n minus 4. Again, so much simpler than what we started off with, which is great. Alrighty. So let's talk some about permutations. Now we talked a little bit about permutations yesterday. Maybe I'm wrong on that one. No, we are wrong. That is a new word. Okay, brand new word for us, permutation. So a permutation is an arrangement of things. If I have, let's say I have these 3 objects in front of me, my calculator, my pen, and this little pad of paper, this is one permutation of those things. When I switch the order, that becomes a new permutation. It's all the same stuff, but I changed the order of it. Here's another permutation of those things. So they're different arrangements. Different arrangements can we have? So a permutation is an arrangement of objects in which order is important. And I'm going to underline order is important because we will do another type of thing here called a combination where order is not important. So we're going to keep having this conversation, like, is order important? Just as a little preface for where we're going. It is the number of ways n objects, we use n and r in this unit, n objects can be placed into R positions. So with the things I had on my desk here, calculator, pen, and notepad, I had 3 things and I wanted 3 positions for those things. But we're going to practice this a lot as we go here. All right, let's try this here. There are 6 people standing in line for a movie. How many ways can those 6 people be arranged in a line? Now you'll notice 6 people, they are not like some kind of genetic, exactly the exact same twins. They are 6 different people, and I have 6 positions for them to stand in line because they're all going to be there, right? We're not leaving anybody out. So here are like the positions in line, like maybe this is where the box office is and this is the end of the line or something like that. Now what we need to do is put these people in order, and we're going to try and figure out how we can do that, how many different ways we can do that. So imagine your 6 people in front of you and you're going to call one of them forward. How many options do you have for that first person? Well, there's 6 people standing there. There are 6 choices for the first person. Then, using the principles that you learned yesterday, we are going to multiply when we have different options. So we already have someone in this line up here, in this position here. There's someone first in line. How many people are left standing in front of you? Well, you've used up 1 person, so there are 5 people left. And then you've used up another person, there are 4 people left, and then 3 people left, 2 people left, 1 person left. And again, we multiply based on the principles you learned yesterday. All right, now does this look familiar? Does this kind of look like 6 factorial? Yeah, hopefully it does. Well, I'm going to use my calculator because, again, I'm lazy. And I can tell that this looks like 6 factorial. So we call this 7 ways. 720 ways. Now another way we can look at this is we could say, using the permutations, we could say there are 6 people and I need 6 people to be in line. So 6 pick 6 is kind of how we say this. Let's try our calculator for that one, and I'm going to show you how to do it in your calculator here. Remember, I showed you the factorial button right there. So mine is right next to it, and it happens to be yellow. Usually they're pretty close together because these are kind of like similar topics. So in my calculator, I have to go 6. Mine's yellow, so I have to hit Shift, that button, and you see a big P there. And then I wanted another 6. So 720. So it ends up being the same answer, which kind of makes sense to me, which is, well, that's what we're going for. So what the saying is, I have 6 people standing in front of me, and I want 6 people to be in line. How many ways can we do that? That's what a permutation is looking for. So flip your page here, and we're going to kind of define that formula for permutations. Okay, so formula, we say n pick r, ooh, it's kind of off there, n pick r, and these are subscripts. They're not just little letters, they're subscripts, so they're kind of smaller and kind of down a little bit, but my writing's really bad, so I have to make them a bit bigger so you can read it. And here's the formula, n factorial divided by n minus r factorial. Now this is a great formula, wonderful, but for the most part, we're going to use our calculators because you always have a calculator in this course. So, you know, why not? So for example, in that last one there, we had 6 pick 6. That means there are 6 people, 6 spots in line. 6 pick 6. Let's give this a try now. How many 3-letter codes can be formed from the letters of the alphabet if no repetitions of letters are allowed? Now that's a really big point here. No repetitions are allowed. That is a part of permutations. If repetitions are allowed, then we cannot use permutations to do this. So we have to say no repetitions are allowed. All right, so let's think about what we have here. How many letters are in the alphabet? I always used to think it was 25, but no, it's actually 26 letters in the alphabet. And I want to have 3 of them. So I have 26 choices in front of me. I want to pick 3 of them. So I just say want. This is kind of my work to myself, you know what I mean? So what we say is, to use this in terms of permutation, we say 26 pick 3. Because I have 26 choices and I want 3 of them. I'm going to use my calculator here. I'm going to go 26 P3. Oh my gosh, there's a lot of different code words that are possible here, aren't they? 15,600. Now, something you'll notice here is that the first number will always be bigger than the second number, or the same at least, but usually this one will be bigger. And if we try to accidentally do it like, ooh, 3 pick 26, you'll get an error, which is helpful because that tells you you're kind of on the wrong track. So this one should always be bigger, or the same number at least. And how does this relate to factorials? Well, we can kind of think of this as, if we want to use the formula, we could say 26 divided by 26 minus 3 factorial. So this would be 26 factorial divided by 23 factorial. And if you wanted to check that out, that would end up being 26 times 25 times 24. Like, I have 26 choices for the first letter, then 25 choices for the second letter, and 24 choices for the third letter. There's a lot of different ways to think about this, and they're all like really good ideas. Okay, let's try another one. How many different student council committees, made up of a president, vice president, secretary, and treasurer, can be elected from a class of 100 students? Now, what I'd like you to notice is, 1, these things are distinguishable, as in the president job is definitely different than the treasurer job, right? These are separate jobs. Each student is a separate student, so it's distinguishable. So they're not like identical things. We're going to get to identical things, but we're not there yet. Also, we say that order matters here, because if you told me, hey, you won president, and then the next day said, oh, actually, you're going to be the treasurer, I would be kind of mad. So I say that order matters because these jobs are different. Or if we're on a sports team and you say, yeah, you're going to be the forward, and then they say, oh, actually, you're going to be the goalie, I'd be like, oh, that's different and that matters to me. So that's why I say order matters here, which is why we're using permutations. In the future, there will be a time when order doesn't matter. And so we're practicing thinking about it now. Okay, so I have how many students to pick from? I have 100 students. I want to fill how many positions? 1, 2, 3, 4 positions on the student council to fill. So we say 100, pick 4. I use my calculator and woo, there's a lot of different ways to do this. 94,109,400 different ways, different committees we could come up with. And some of those committees, it could be the same 4 people, but maybe they're in different positions. I don't know why I did that with my fingers, but maybe one of these committees has these 4 people, and then we just move their positions. That would still count as a different permutation. So it's a really big number, but some of these committees are really, really similar to other ones, right? Let's keep going here. And I think this is our second last one for today. Okay. Ms. Benarski has 10 students in a grade 9 math class. They all need to do a presentation in front of the class on a math topic of their choice. How many different ways can Ms. Benarski arrange them to do their presentation? Okay. So notice it says how many different ways. Those are kind of like some keywords to tell us that this is a permutation. So I have 10 students. Does every student have to do a presentation? Yes, I think so. So I want 10 students to do their presentations. So we say 10, pick 10. Using my calculator, whoops. There are 3,628,800 different ways these students could go in order and do their presentations, which is a lot of ways, isn't it? It's a lot of ways, a lot of different permutations. All right, one more, and this is kind of a step up. This is a level 2 or 3 question, maybe. Okay, and our last one for today. Angela needs to create a password for her Edsby login. The password can use any digit from 0 to 9 and or any letter of the alphabet. So we, regular passwords. The password is case sensitive, so she can use both upper and lower case letters. That means that a capital A is different than a little a. A password must be at least 2 characters and a max of 4 characters. And each character can only be used once in the password. So this is really key for us to be able to use permutations, because if repetition is allowed, then we can't use permutations. How many different passwords are possible? Now this is where it gets tricky, and this is why this is a step-up question, is because I don't know if this password has 2 characters, 3 characters, or 4 characters. And we call this a case question, where 2, 3, 4 characters are going to be our cases. So I'm going to write that down here. There are 3 different cases. Put that in quotation mark because it's, I don't know, it's a good idea. Okay, case 1. That would be 2 characters. Case 2. 3 characters. Case 3, 4 characters, and that should cover everything we want to talk about. What we're going to do is we're going to figure out how many ways can we do each of these ways. Like how many ways can we do 2 characters, 3 characters, 4 characters. And you'll notice what we're talking about is or. Like a password has 2 characters or 3 characters or 4 characters. And when we're using or as our language, we add. So we're going to find each total and add the cases together. Because 2 characters or 3 characters or 4 characters. Now, let's get started, but let's do a tiny bit of thinking before we do. How many digits are there from 0 to 9? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 10 digits possible. How many letters are there? There are 26 lower letters and 26 upper letters. So I have 10 plus 26 plus 26 choices of letters or digits, right? I have 62 characters to choose from. 62 things that I could like put in my password, because we're not including all the other weird things you have on your keyboard. Okay, so case 1, case 2, case 3. My writing is getting worse as we go here, but that's okay. Okay, 2 characters. So I have 62 characters at my disposal, and I want 2 of them. So we say 62, pick 2. I'm going to use my calculator, and I got 3,782. There's almost 4,000 different passwords, which is actually not that many in terms of passwords, right? But it's a few. For case 2, I have 62 choices, and I want 3 of them. So we say 62, pick 3. And this is going to be much bigger because we have 1 extra character we're using. Last case, I have 62 characters again, and I want 4 of them. So 62, pick 4. This time, much bigger again because we have a whole other character that we're willing to use. 13,388,280. Now to finish this question off, I want the final answer here. So in total, I'm going to add these things together because I'm saying there's this many, or this many, or this many, depending on how many characters we're using. Add them all together, put them in my calculator. I got 13,618,982 different passwords, which is a lot. Now imagine putting all the other letters and not letters, but all the other symbols and stuff, putting that into the game. That would make there be a lot of different passwords, right? Alrighty, that's it for today. Thank you.